Hello everyone. On behalf of Schneider Electric Solar and myself, welcome to Battery Technologies for Solar Applications. My name is Mike Mui. I am based out of two beautiful cities, Vancouver, British Columbia and Denver, Colorado. And I'm happy to chat with you folks today about batteries. We're going to be talking about some general information, the capacity ratings that are a little bit confusing sometimes, how to charge batteries properly, the types of batteries we work with, how these batteries work in off-grid applications, pure off-grid, versus if you have grid-connected DC-coupled applications, or if you've got a AC-coupled application as well. I encourage you to check out our offerings and solutions at sesolar.com. All our owner's manuals are there, firmware updates, application notes, lots of good stuff in there. Talking about batteries real quick, this stuff here, chemistry, basically we're taking electrical energy, tucking it away in chemical energy, and then doing the reverse. This is how a lead acid battery works. When this happens in a single reaction chamber, we call that a cell. It could be a plastic box or it could be a lemon. You've seen that on YouTube. And batteries are a bunch of cells in series to get the voltage that we want. And then a bunch more to get more current. And then a bunch of those, we call them a battery bank, big stack of batteries. So batteries and cells have this nominal voltage that we all are familiar with, 1.5 volts flashlight battery, 2 volt, lead acid battery, 3.7 lithium battery, 6 volt battery, or cell, 6 volt battery is usually 3 of these cells, 12 volt battery usually 2 of these, or 6 of these. And this so-called voltage is always lower than the typical full, what we call rest voltage, and definitely lower than the charging voltage. You need way more than 12 volts to charge a 12 volt battery, and a full 12 volt battery should have more than 12 volts on it. But when I say more than 12 volts on it, that gets us confused again. That gets us confused with a thing called state of charge. State of charge is actually what tells us if the battery is full or not. You can think of it as the actual volume of stuff in this container. But if you think about it, we don't actually measure the volume of things, say, in the kitchen. We measure the height of the things in this piece of technology called the measuring cup, right? So we're measuring height, not volume. And so we get used to using this voltage thing as a measure of how much you actually have in there. And that's not a good measure except under complete rest. And on a battery, that means you can't be charging it and you can't be discharging it. Because if you're shaking it around like that, that measure is no longer accurate. It doesn't accurately tell you the actual state of charge of the battery at this point. So let's talk about the ratings, because we are used to buying 12 volt batteries, 1.5 volt batteries, but the other big number is the amp hours. Just like when you buy a car, what's its fuel economy in liters per 100 kilometers or miles per gallon. But this is one of those specs that's only accurate under very certain conditions, just like the fuel efficiency spec, right? And the major condition is how quick are you discharging that battery? Are you expected to have that battery last for an hour, like in a computer UPS? Are you expecting that battery to last the whole day, like a cell phone? So it'd be really nice if we could figure out how long the battery will last by just taking the amp hours and dividing by the amps. So if I had a 100 amp hour battery and 100 amps out of it, it should last for 1 hour, right? But no, unfortunately, that's just not how it works. It gets more complicated, lots of funny math here. Basically, it says that the more current you draw out of the battery relative to the size of the battery, the more the battery is going to shrink. And fortunately, a good battery manufacturer will do the math for us, and he will give us honest ratings like this one here. All right, let's look at this thing here at this 20-hour rate. It's 225 amp hours, which means 11.25 amps times 20 hours. So if we're drawing 11.25 amps out of it, we could do it theoretically for 20 hours. But let's look at this number over here, the 2-hour rate, 146 amp hours. That's 73 amps times this 2-hour number here. So that tells us if we were drawing 73 amps out of it, we can only do that for 2 hours. So the amp hours actually shrank. So if someone tells you what the amp hour capacity of the battery bank is, you're hoping that they're also telling you the rate, because you don't know if it's this or something way over here. In the solar world, generally, we will use the 20-hour rate. That's what we're going to be commonly referring to. So we normally are running at 48 volts or 24 volts sometimes for our thing, but you don't buy 48-volt batteries. You have to make them up out of 12-volt or typically 6-volt batteries usually. And that leads to some confusion on this amp hours capacity in your battery bank when you arrange the batteries like that, big stack of batteries. Theoretically, we know if we just knew the amp hours, the capacity, and the voltage of the battery bank, we multiply them together, and that gives us the energy of the battery in watt hours. And when you buy lithium batteries or other advanced batteries these days, they actually will specify it in watt hours and kilowatt hours. But in the lead acid world, they're generally going to stick with amp hours. So for example, if we had a 225 amp hour battery bank at 48 volts, that gives us basically a 10.8 kilowatt hour battery bank. In the lead acid world, we're always assuming 24 to 48 volts. To determine the amp hour capacity of a battery bank, the best way to do it is you basically look at the energy of one of the batteries, multiply by the number of batteries, and that gives you the total energy. And then you divide that by the voltage of the bank. And run through a quick example here. We have 8 6-volt batteries, each of them 100 amp hours each, arranged in series, 8 of them. So one of these batteries is 600 watt hours. I have 8 of them, so that's a 4.8 kilowatt hour battery. Divide that by 48 volts. So this is what we would call a 100 amp hour battery at 48 nominal voltage. Similarly, if we arrange the batteries differently in a 24 volt configuration, we still have 8 600 watt hour batteries. We still have a 4.8 kilowatt hour battery bank, but because we've got this arranged in 24 volts, this is now a 200 amp hour bank at 24 volts. So be careful how you actually consider what your battery bank is rated for in amp hours. Energy in kilowatt hours doesn't change. Let's talk a bit about charging batteries. To get a battery to actually charge, you have to take it well above its nominal voltage. So if we had a 48 volt lead acid battery bank, we have to take it way above 48. We have to take it up to 47.6 volts. We call this the gassing voltage. We do this by putting in as much current as we're allowed, 100% of what we're allowed, and the battery manufacturer has to tell you this. And as we put in this constant current, the voltage rises up, and then we get there. We call this the bulk voltage. This stage is the bulk stage. In the lithium world, they call this the constant current stage. And then next, once we get there, we start reducing the amount of current. We just trickle in as much current as we need to keep the voltage up there. And the amount of current that we need decreases as time goes by in order to keep that voltage there. We actually got about 70 or more % of the energy of the battery over here in bulk stage pretty quick. But that last little bit needs time to do. It's kind of like it's got a brand new cheap plastic sponge in there, and it takes time to actually absorb the water. So that's why we call it the absorption stage there. You can't rush this, unfortunately. So we do our very least to keep the voltage there. And then when we notice that we don't need hardly any current anymore, a certain threshold, then we say we're done. At this point, the battery is nice and fully charged. Optionally, if we enable something called a float stage, we set it at this lower voltage here, and that prevents the battery from discharging. Doesn't actually charge it, but prevents it from discharging. Some lithium batteries don't like this. I want to talk about cycle life of the battery because that figures heavily in battery economics. Think about a paper clip and bending it back and forth. I mean, the deeper and more often you bend the paper clip, the sooner it's going to break. Bend it a little bit, you could do it a lot. Bend it really, really far, it'll break really quick. And a battery kind of wears out like that. The deeper you discharge it, the quicker it's going to break. And the more often you discharge it, the quicker it's going to break or wear out. When batteries wear out, they just start looking smaller and smaller. They run for way less time. They seem to charge super quick. Your cell phone does this after 1 year, of course. This is your typical graph for a lead acid battery. It tells us that if we flatten this lead acid battery, it will last 100 times before it breaks. If we only half discharge it, then we can get 1,000 cycles. So this is what people generally try to target here, this 1,000 cycles. It's a bit of an economics exercise. So we can get 1,000 cycles at a 50% depth of discharge. And let's say it's a 48 volt bank at 220 amp hours. That gives us a 10 kilowatt hour bank if we multiply that together. And it costs us $2,000, just round figures. But that math tells me that this battery costs me 40 cents a kilowatt hour every time I use it. Every cycle costs me 40 cents a kilowatt hour. So this is even if the energy to charge it was free. So you may think like it's a good idea to discharge your battery, but maybe not, depending on, if you are on the grid, if you can choose, and you have to think about this. You have to do the math yourself, of course. So let's talk about the common battery types we're going to use. The lead acid battery, of course, is the most common type. It's well established and the cheapest, and it's very, very recyclable. You can reuse almost every little bit of it. There's two broad categories I want to get out of the way with first. There's deep cycle and starting batteries. Deep cycle batteries have a bunch of thick lead plates. Thick lead plates don't wear out if you try to deeply discharge the battery. Think of it as like a marathon runner. Starting batteries, however, they have to have a whole bunch of thinner plates because their job in life is just to deliver a whole whack of current really, really quick to turn over that starter motor. Think of it as like a 50-meter sprinter. But if you discharge this battery deeply, you will basically completely wear out those plates. And once those plates are completely dissolved, they don't come back ever. So that battery's dead. So you don't use starting batteries on an inverter. Deep cycle batteries will have an amp hour rating. If you see a battery that has a cold cranking amps rating, that's a starting battery, so you don't use it. When I talk about lead acid now, I'm always talking about deep cycle. Amongst those types, the flooded was the first common type. Use liquid electrolyte, distilled water, but you've got to replace that water regularly. You can do this little thing called equalization sometimes to perk up the performance again, but they're subject to spilling and freezing, but hey, they're cheap and durable. There's a gel battery, which was the first type of sealed lead acid battery. You could use them upside down, but they were expensive and you couldn't equalize them, and they were picky on how they were charged and discharged. The AGM, the absorbed glass mat battery, is really common these days. It uses solid electrolyte. It's kind of a compromise between these two. Lithium, of course, everybody is talking about it these days, but that's expensive for sure. But they do give you more cycles and deeper cycles than lead acid, so the math changes. The voltage also doesn't fall as much as lead acid when you discharge them, so the voltage stays pretty flat as it gets more and more empty. The problem is they're volatile. If you charge them with too much current or voltage, bad things can happen. If you just discharge them too quickly, then bad things can happen. We didn't really worry too much about lead acid for that, as long as the wire was good enough for it. If you unevenly charge the cells inside the battery, then we can have a problem. If you physically damage it, you have a problem. So lithium batteries, you got to be really careful. Any battery used on our equipment, the battery manufacturer has to say that it's compatible with our equipment. And it has to have a BMS, a battery management system, which is responsible for the safety of the system. It has to be the fail-safe. And they have to be able to tell you how to program the equipment properly. What's the maximum amps that you can take out of there before the contactor will complain and open up? Does it like a float stage? Do you want 2-stage or 3-stage? And what are those voltages? Right? They have to tell you this. So I want to talk about this BMS, this battery management system, because it's real important. Our equipment only connects up to the positive and negative. That's all we really see. We see the voltage on the outside. That's all we really see. And with a lead acid battery, we weren't really worried about how all the little 2-volt cells inside the battery shared. When the battery wore out, it wore out. A lithium battery, though, the lithium cells have much less of a sense of humor than a lead acid cell. Because of that, they have to have the battery management system here, looking at every single cell to check if it is being charged and discharged evenly. And if it's not, then it has to take some action, basically open up the contactor and say, sorry, you can't use me anymore. Just like if it gets too hot, it's looking at the temperature. Just like if there's too much current flowing through, it's going to open up. It's also got this little circuit here for when you first connect the battery, the spike doesn't trip this thing. So you need to have a BMS. But don't confuse BMS with this thing we have called the Connect Battery Monitor. That's a different thing. Again, you have to make sure to follow the instructions from the lithium battery manufacturer on all things. We use battery temperature sensors. We give you one with every thing that we have that charges batteries, but don't use these things on lithium batteries unless the battery manufacturer tells you to. Some of these lithium batteries, they come in 12 volt or even maybe 3.7 volt packs, and you have to individually charge these really carefully before arranging them into a 48 volt pack. So an extra charger is needed for that. You got to talk to your battery guy for that. And ensure the battery charge and discharge parameters are set properly, and make sure that BMS can handle the initial connection current to the inverter. Because inverters have a lot of capacitors on the input, and when you first turn it on, it's going to draw a big whack of current. So you've got this typically inside the BMS's pre-charge resistor that basically connects it first to slowly charge up the capacitors, and then connects the main contactor to connect the battery to the inverter. This is the input capacitance of our inverters. That's what they need to know. So let's talk about how we use the battery banks in your off-grid applications. Typical household energy consumption looks to be kind of like this. Grid connected, homes with air conditioning started about here. Off-grid, typically though, you want to be in this range down here. So let's look at this little exercise here on some typical appliances for someone who's maybe finished. These appliances have a power rating here in watts, and that's one thing. But the other thing you need to consider is how often you use something like this. So something like the stove or the oven, you're maybe using 3% of the time. A microwave, 1200 watts, but only 2% of the time. But something like a fan, 100 watts for 50% of the time. We have this number here that we're going to call the equivalent continuous watts here by multiplying the actual power by the duty cycle. So if we look at these appliances, looking at the equivalent watts, something like lights here, which were 11th in terms of how much power they draw, they're now only 7th in terms of how much actual energy they use. So you have to think about how often you use it as well as how much it uses. So if you're designing an off-grid house, you'd probably look at things like getting rid of your stove and oven and running it on propane, and your sauna would probably be propane or wood, or your dryer hopefully would be propane to get rid of that. Looking at what we have left over, it's looking like we have 5,750 peak watts for this equipment, and that's 528 equivalent continuous. So we have to make sure that our inverter can handle this with ease, but this is what tells us how big our battery needs to be for how long we want to run. So if we did the math, that gave us 13 kilowatt hours per day of energy consumption. And 13 kilowatt hours a day divided by 48 volts means we basically need 300 amp hours there. But that means killing the battery. We can do that 350 times. So we don't want to do that. So we're targeting this range here, 50% depth of discharge. So that means we should have a 600 amp hour battery bank if we're talking about 48 volts. We would say that if we had a 600 amp hour battery bank, that would give us 1 day of autonomy. That means you could do that regularly, a 50% discharge. We would say you'd have a 2-day emergency autonomy, the zombie apocalypse kind of thing. You're not worried about the life of your battery bank. And as you increase your battery bank size, that gives you more days of autonomy, your normal days or your emergency autonomy. Let's talk about battery banks in grid-connected DC-coupled hybrid applications that we call them. This is where we have a solar charge controller charging the battery and a hybrid inverter using this energy in interesting ways. It could be sending it back to the grid or mixing it in with the grid to use your loads and things like that. So there's different considerations for the battery bank in this case. It kind of acts as a pump, pumping energy out of the battery. And you think about it, the pump is controlled by this little switch here connected to this float valve. If this container was kind of tall and thin, just a little bit of water in and out is going to make it bobble around really quickly. But if it was a big, wide tub, a little bit of water in and out isn't going to make the height bobble around very much. It stabilizes the system. For this kind of use, you do need to have a reasonable sized battery bank to stabilize the system. Otherwise, you could have things like when clouds roll around, your export starts cycling around and things like that. For stable operation, we're going to recommend about 1 watt-hour per inverter watt as the minimum to stabilize the system. Don't undersize the battery bank. Even though you think that your main use is just for self-consumption or export, don't undersize your battery bank. And you also want to consider your battery economics before using a feature like load shave. That's the feature where it allows you to dig into the battery, discharge the battery in the evening, charge it during the day. Sometimes it makes it worth it, but if we look at the math that we did earlier, you have to do the math yourself. Finally, I want to talk about using battery banks in AC coupled applications. That's becoming real popular these days. In an AC coupled application, we basically have our good old XW here providing, actually in this case, we have our solar array feeding a grid-tied inverter, which feeds into the load panel, which actually feeds right through to the XW, selling power to the grid. Also, any loads connected to this load panel, of course, are being serviced before it gets there. When we lose the grid, though, what happens is the XW does its job and keeps this load panel up and running. And at this point, this grid-tied inverter, which is normally grid-tied, it should go away. It doesn't even know that it lost the grid, so it keeps running, and it can still run the loads. Otherwise, normally with the grid-tied inverter, without this XW, with no power, it doesn't matter how much solar panels on your roof, this won't work for you. What we need to be careful about, though, is what happens in this case when we have not very many load, but a good amount of solar coming in from this grid-tied inverter. This extra energy, good news is we are storing it away in our batteries, but that's good news and bad news. Is this too much current for this battery bank? And with lithium batteries, we have to be super careful about that. The bigger the battery, the more amps it can safely handle. The bigger the bank, the better. But you have to make sure that the battery bank is big enough for sure that the maximum power of the PV inverter does not exceed the maximum current rating of that battery bank. And that's the biggest consideration that you have to take into account. Let's talk a little bit about maintenance. The battery manufacturer's instructions will always tell you how to maintain those batteries. Things like rechecking the torque on all battery connections regularly is important. We're talking about high amounts of current generally, so a lot of thermal cycling. Things get hot and cold, and they're going to get loose after time. Flooded batteries, of course, have to be topped up with distilled water regularly. Distilled water only. Anything else will kill them. Charge the battery properly with a multi-stage charge. Flooded batteries, sometimes you have to do the equalization charge. Our equipment can do that if you tell it to, but always check with the battery manufacturer before you do that. And that is all I have for you folks. I hope you got something out of it. If you folks have any questions, please enter them into the chat and we'll see what we can do. I have a question about what CC and CV meant. And I mentioned, I think, really quickly earlier, CC stands for constant current. And in the lead acid world, we generally call that the bulk charge stage, the first stage. We put in a constant current, the maximum that we're allowed to, until we get it up to that bulk voltage. So in the lead acid world, we called it bulk, but in the lithium world, they kind of call this CC, constant current. And then when we went to the next stage, the absorb mode, we were at that constant voltage and the current was decreasing, but the voltage was constant. We called it absorb, but in the lithium world, they would call that CV, constant voltage. Somewhere along the way, someone got mixed up and then they started calling things CVCC. And the term CVCC kind of stuck in the lithium world, when in fact, the order is actually reversed. It's kind of one of those Luke, you are my son quotes. It was close enough, so everybody just ran with it. About training on Connect XW related products. Again, sesolar.com has links to some of our available webinars, and there's a good amount of webinars there's a good amount of training videos, long and short, on YouTube as well. But once again, thanks everybody for attending. I really hope you got something out of it. Have a great day.